Swayam Prabha. Digital India. Educated India.
So we looked at the NFV framework that enables dynamic construction and management of the virtualized network functions. Now let us look at the key architectural components of this framework and what are all the key abstractions and interfaces that would be necessary to realize such a framework. And in this, IIT came up with what we call as the IIT NFV reference architecture, also known as the NFV MANO or the IIT NFV management and orchestration reference architecture. And again, the components that we saw earlier to the components that we see now are more or less the same, but there are some additional components that we need to discuss in detail. First, this NFV architecture that was proposed by IIT has in fact helped define the standards for NFV implementation. And so we need to understand what are those standards. And it would not be possible to cover all of them to the greater depth, but at least we should try to understand what are the main architectural reference points and what are the executional reference points that are being leveraged to build this reference architecture. And in essence, this NFV reference architecture consists of, at the core, the virtualized network functions or the software applications that would be deployed to deliver the desired network functions on the NFV infrastructure. So we looked at NFV infrastructure encompassing as a virtual storage, compute, and virtual network, including the hardware infrastructure of compute, storage, and network. But when we think of these virtual network functions that are going to be deployed, then we need to ensure that these network functions are managed properly. And to do that, IIT came up with what we call as the EMSs or the element management systems, which would be responsible for the functional management of these virtual network functions. And in this, by management, what we mean is to include the functions of fault management, the configurations that we need to set for VNFs, what is the the compute requirements, storage requirements, memory requirements, all of these configurations that you would want to do, the performance monitoring, what are the performance characteristics that you are looking for, what are the SLAs that this VNF needs to be supporting, and what are the security constraints in terms of access control, authorization aspects. All of these configurations can be plumbed into what we call as the element management systems. And note that these element management systems can themselves be deployed as the virtual machines or virtual instances that would run on the same infrastructure. But this would provide us the handle to control and configure the network appliances that we would want to run. Although in this figure, what we have shown is that there is one-to-one mapping for element management system to the VNFs, but this is not necessarily true. We may have a single EMS which is able to be managing multiple of the VNFs. So one-to-many is possible in terms of multiple virtual network functions being managed by single EMS instance. And now these EMF instances or virtual network functions need to be managed from the network operator point of view. And for a network operator, you would want to have a control from one place to say how these configurations can be done. So for that, this interface of virtual elements to the virtual network functions, the MANO infrastructure that we would want to facilitate need to be given. And this interface is between the core layer of what we saw as the MANO layer. Within this, we need specific functions, what we call as the virtual network function managers, which would manage the subset of these network functions, because one of the kinds of network functions can be deployed by some software vendor, while the other kinds of network functions may be coming from other kinds of a software vendor. So we may have different virtual network function managers to manage all of these different kinds of virtual network functions. So in essence, this VNF manager is responsible for the lifecycle management of these virtual network functions and the configurations on the EMS. And when we mean by lifecycle, what I mean is when to instantiate this network function, when to have the software updates for these network functions, how to version these network functions, and ensure that you can monitor the performance levels, diagnose the faults, and if there are any failures, how to heal or ensure that they can be respawned, and when their life cycle is over, how to terminate these virtual network functions. All of these become the key aspects for this virtual network function managers to handle. And once we have provided this virtual network functions to the virtual network function managers interface, that would enable any open environment so that multiple managers can be plumbed in on a single infrastructure. Second, like we have at the bottom is the network function virtualization infrastructure, which encompasses both the virtual and the physical infrastructures. This again, when we want to be controlled, or like when we have a premise or a campus or enterprise, we have these infrastructures that are going to be set up. We need a handle to again manage this infrastructure. And that's exactly the role of virtual network infrastructure manager, or what is being termed as the VIM here in this diagram. And this virtual infrastructure manager is responsible for managing the compute, storage, and network resources, both software and virtualized software or virtualized infrastructure, as well as the physical infrastructure. Then what we would also need is to see that how these network functions can be brought to life in terms of to manage the life cycle. There have to be some policies on which you would want to act. And that's facilitated through the component of what we call as the NFV orchestrator in the Mano. And this NFV orchestrator is basically the one that automates the deployment, the operation, the management, the coordination of the VNFs. When we spoke about how to chain these VNFs, what are the means to connect these resources, all of this could be coordinated from this NFV orchestrator. So this NFV orchestrator basically covers the orchestration and lifecycle management of the physical as well as the software resources that are needed to run these virtual network functions. So that means this NFV orchestrator would need to communicate with the virtualized infrastructure manager on one end, and also need to communicate with the VNF managers to spawn or create the necessary virtual network functions and set up the configurations, etc. on them. Thus, this NFV management and orchestration focuses primarily on all virtualization specific management tasks that are necessary to run this NFV framework. And here we can also see that there is a role of an SDN controller, although the placement of an SDN controller in terms of the architecture of NFV was highly debated. But SDN controller, like we saw in our earlier lectures, is to manage how we want to set up the communication amongst these network instances, is to manage or provision the resources or these virtual computes that we would want to build in this NFVI. So we can think of SDN controller is working in conjunction with the NFV orchestrator to set up the forwarding rules that we want, what control functions that we want to build for these, what is the topology that we want to build with the virtual links. All of these aspects can be managed by the SDN controller, which we can think of as being situated along the lines of NFV orchestrator and the NFV Mano framework. And the other most critical piece that any of the operations in telecommunication or enterprise would have is what we are showing here as the OSS and BSS component. And in OSS and BSS, what we mean by OSS is the operations support system, and what we mean by BSS is the business support system. Think of operations support system as a means to facilitate the communication, to facilitate the concerns, whatever we need to deal from an operator point of view to manage all of these resources. And from this end, what we would see is basically that the means to maintain and operate all of these devices, we need specific database where the things would be basically stored in terms of what informations we are gathering about the infrastructure, gathering about the services that we want to build and operationalize these services. And think of this operationalizing as taking care of the entire infrastructure that we have and to ensure that we meet the utility over this infrastructure. Like when we have a telecom operator who is trying to onboard a new user, what is his status that is being maintained for a given user on the local premise is managed by the operations support system. And the other aspect is the BSS, which primarily consists of how to interface with the customer or the end user. Like if there is a customer relation management information that needs to be set up, like when we talk over our mobiles or when we use the data, there is a billing that happens. So how this telecommunication billings that need to be done, given and updated to the user, all of these aspects come into the business support. So think of, in a very simple terms, if we have to say the interface, for example, between the BSS is for capturing the user's requests or capturing the order from an user. Like user specifies the intent to the networks through this BSS framework. And how you realize such an intent of an user, like user wants to have 100 GB data that he wants to purchase. That's done through the BSS support system. Now, once that is done, how it is being operationalized and ensure that the requests of a user are fulfilled is what governs what we call as the operations support system's role to fill in and do this job. And this is where like the reference points of this OSS and BSS, how they interact with the virtual network functions and how they interact with the virtual network infrastructure hardware have been categorized as other reference points for communication. Note that the communications that are marked in green, that are the execution reference points for the VNFs to interact with the hardware and EMA. Likewise, for the virtual layer to interact with the infrastructure, that's the software abstractions that we are trying to build for the VNFs to work on a given infrastructure. And the main NFV reference points, or the ones that are marked here in black, are the ones that allow us to manage and control such an infrastructure and build the desired services over this infrastructure. And whenever we have such an infrastructure's requirements, we need to catalog a lot of metadata. And that means there is an implicit requirement to support the database where we catalog the infrastructure, the kinds of network functions, the service descriptions, all of this data in one fashion. This could be even a distributed framework by itself. Overall, this was how the ETSI NFV reference architecture was delivered from the ETSI group. The ETSI NFV reference architecture saw various open source implementations, and we'll look at just one of the open source implementations known as the OPNFV, which it stands for the Open Platform for NFV. And this is a collaborative project under the Linux Foundations, and that has helped transform the global networks through this open source NFV. And what this OPNFV tries to do is to facilitate the real implementations of the reference points that we discussed in the earlier framework or the reference architecture. And it initially started with the focus on the virtualized infrastructure manager, implementations of how to communicate or bridge this interface between the virtual infrastructure manager and the network function virtualization infrastructure as a key piece, and then it started to build all the other components. And this OPNFV, which facilitates the common NFVI and also facilitated through the project as a continuous integration with several of the upstream projects. And when we say what were the core upstream projects that we see in this architecture, where they were having the means to develop and deploy network functions. And primarily it is the OpenStack that was there already to create VMs, orchestrate, and where to deploy the VMs. So this OPNFV was trying to support integrating this NFV framework, which is by developing the VIM and the NFVI, with integrating them with the upstream projects like OpenStack. And when we think of the containers, we could have the Kubernetes as a framework that would support. And when we think of the controllers, SDN controller, they used to support the Open Daylight and many other like ONOS and so on. So the goal was to build this reference platform which any of the telecommunication operators or even the enterprise operators could take and start to build the NFs and work them out. And this has been a huge success, and it's continuing. Although it started with just the bottommost layer, it has now grown to address the VNF manager, the orchestrator, and the interfaces between these points. Further, there is also this cloud band and the Red Hat architecture. This is infrastructure based on how the Red Hat Enterprise Linux OpenStack integration could be done with the cloud band, which was an Alcatel-Lucent based NFV platform. And this in a way offers a new way to design, deploy, and manage the network services. You can think of having the Red Hat OpenStack, which is now facilitating how to manage and provide the control over the NFVI and implement the NFV manager, and also provide the cloud band orchestrator communication with that to build the VNF models. And Tosca is one of the core protocols or mechanisms to see how the NFs can be modeled to build the abstraction, the logical abstractions of providing the services that we want to build for realizing these network services. And these have been very prominent and successful, and there were many more of these architectures that have been instantiated. But we need to see, okay, we have this framework architecture, we have so many of the reference implementations, but what exactly do they offer in terms of what are they bringing to the table? And as we know, this NFV is about implementing the network functions in software, which would now run on the generic hardware, right? And in order to do this, we need to say, when we create a framework to instantiate these network functions, we are thinking of a data center or a cloud-like environment where multiple users are using the same resources. That means we need to ensure that the framework implementations that we have are able to support multi-tenancy. And what we mean by multi-tenancy is basically an architecture where a single instance of software application or the hardware that we have would serve multiple customers. And each customer is what we refer to as a tenant. And in this reference, the mode of operation for the software where multiple independent instances of the same software could be run by different tenants. And we still need to ensure the isolation for these software infrastructure, but they may still be using underlying the same shared environment. So a logical isolation amongst multiple instances of the same software that we are going to run is to be guaranteed. And this is where the NFV really helps by ensuring that we are able to decouple the hardware from the softwareized instances. And each of the softwareized instances can now be controlled and configured independently by different vendors. And that's how it supports multi-tenancy. And another important aspect, whenever we try to build the systems, we evolve. And when we evolve, we start versioning the systems. And then when we expose these to the public, there may be a need where one user would want to operate on a particular version, while another user would want to operate with a different version. So there is also a need to support what we call as multi-versioning, which allows the network functions of different versions to coexist on a same framework. And this makes it also simple whenever we want to have upgrades or have to switch back to a stable version when something experimental is not working. We could have the previous version rolled back much more simply rather than having to restore the entire infrastructure. And thus, this NFV, through the use of VMs and the right abstractions, enables to support these cases. Further, this NFV also we discussed saying that it would allow for having some sort of a resilience and service assurance, and also ensuring that there is a security diagnostics and surveillance that we could do with these functions. So our reference implementations that we want to build and the architecture need to have the abstractions or the APIs to facilitate these informations. And overall, when we have such a framework, what it really creates is the opportunity for many of the software players to come together and independently even build different network functions. And this is where the innovation starts to foster in terms of how different software frameworks can be pulled together and create the new services, and even collaborate with different network functions to create multiples of these services to work. And in doing all of this, now what this NFV really tries to facilitate is to provide a scale for deploying a large number of instances, meet the demands of the traffic load to scale out or scale in the required instances of the network functions that we would want to run. And all of it can be automated in terms of trying to building a new instance of network function, managing its life cycle, scaling the resources or even scaling up the resources of CPU or memory or requirements for a particular function can all be done in an automated fashion. And thus, what NFV actually offers is to ultimately transform the way we can think of the role that the network operators have to do in terms of building the network infrastructure. But note that this is often always has to be incremental. We cannot have a 0 day where we shift to this NFVI. So they may still have to deal with the legacy hardware, but when it comes to the NFV infrastructure, they may be able to automate many of it and mix and match in their infrastructure as they see fit. Thus, what this NFV essentially offers is, in terms of economy, it reduces the capital expenses and ensures that we can run multiple of the network functions on the same hardware. That's through the consolidation of equipments, which otherwise would have been, you will have to purchase proprietary and different kinds of equipments. Second, it also helps enable the speed for the time to market, and that's where the acceleration for innovation has been really upped by NFV, wherein we minimize the time that the network operator would need to deploy, prototype an idea, because he is no more dependent on the hardware operation equipment manufacturers. Third, through the support of multi-versioning and multi-tenancy, we are able to now allow many of the platforms to coexist on a single infrastructure. So that's a consolidation of multiple infrastructures as well. So it's again adding to the economy of scale, saving on a lot of the aspects of capital expenses, and also from the user point of view, it also saves a lot of resources and money. And overall, this has enabled the open ecosystem for innovation and also provided the flexibility to the network operators to easily manage, readily deploy, provision new kinds of resources and also provide better operational efficiency, wherein now they can take advantage of the uniformity in how you want to manage the resources. You no more need to dig into the different specs of different devices to just manage them. Management is one point. Although the configurations and updates may require you to deal with the specifics, but in terms of the operational management, it would have been a lot more simpler. And overall, what NFV has tried to do is provide the software-oriented network functions which are open to innovation, which we can rapidly prototype and deploy and test out. And in a way, we have basically deossified the network infrastructure and enabled the network functions to take over and softwareize these networks. And all of this also accounts to a lot of operational expenses minimized due to the fact that we don't have to have specialized labor to spend on. We have less of a power. You are not having multiple of the instances that would run for different purposes, but just a commodity hardware running multiple instances. Lower requirements on the space to host and deploy these instances. And also in terms of monitoring, now the number of devices have gradually shrunk, so you'll also be able to monitor these things very easily. And all of this in a way is good, but it also means that we have now in a way tried to cap off on how the IT-oriented skill set and talent can be reused for managing of the NFVs, because they are now built on the commodity hardwares. And we can also see it as an augmentation that it is trying to bring for the IT skill set to operate on the NFVs and build these NFVs very easily. So this NFV supports a lot of use cases, like we said. And if we have to start with the basic switching elements, that's basically in the telecommunication operators world, we can have a broadband network gateway, or the BNG, which is basically the access point for the subscribers through which they connect to the broadband network. This can be deployed as a virtualized network function. Carrier grade NATs that we also discussed earlier can now be thought of not as dedicated hardwares, but as just the network functions that we can deploy on the commodity hardware. And more so, we can even deploy just the routers as the instances that we can run on the commodity hardware as just the softwares like Quagga that the Linux world offers can be used to run the different router configurations that we want to build. And when we see from the mobile network operators point of view, in the mobile network infrastructure, we can implement basically what we call as the HLR and HSS modules, which are basically the home subscriber servers, which is basically in the 4G kind of a network, where the main function that they would provide is to facilitate the communication of the network with the subscriber's profile and authentication informations for a 4G user, and likewise maintain this information as a software instance rather than as a dedicated hardware. And we could also have what we can think of as the GPRS nodes, SGSN, or the serving GPRS support nodes, which are used for basically ensuring that all packet switched data within the network is able to operate and authenticate the users. And this mobility management, all of these specific functions which were earlier implemented as proprietary hardwares, can now be implemented as just the softwares. And likewise is the SGSN, or the serving GPRS support node, which would also can be implemented as a software instance. We can also have the GGSN, or the Gateway GPRS support node, which basically responsible for the internet working between the GPRS network and the external packet switched networks like the internet to speak of, wherein they keep a record of the active mobile users who are attached to the SGSN network and facilitate for the mobility of these mobile users. So all of these functions, which were earlier the proprietary hardwares with custom protocols that were being built, can now be built as software functions. Likewise, the packet data network gateways, which are the critical network functions in the 4G mobile core network or the evolved packet core EPC networks. Hence, we can see that NFV can be applied for the ISP networks, for the telecommunication networks, including the home networks where the ISPs can run specific functions as the whatever the gateway devices that we would use to hook to the internet can now be seen as the virtualized instances where they can provide numerous home services for home environments. And in fact, when we connect with the enterprise networks, we typically use the VPN gateways or IPsec based VPNs. Now all of these functions can be implemented in the enterprise network as the virtualized network functions rather than as a dedicated hardwares, which cost in several hundreds of $1,000s. Also, for any kinds of a network, be it data centers, be it the enterprise or telecommunication, if we want to do any traffic analysis like DPI or quality of end user experiences, all of these measurements that we have to do, they can be built as custom functions and not necessarily have to be dedicated hardware, including monitoring for the SLAs, diagnostics that we want to run, all of them. So in nutshell, we can see the NFV to replace many of the custom or proprietary hardwares that otherwise were deployed in any kinds of networks, including the firewalls, virus scanners, IDS, spam protections, and so on. So all of these become the key use cases for NFV where they can really transform the way we operate with the networks. In essence, like if we look at this NFV use case as a carrier grade NAT, we can build the NAT44 function, which is a software function that would manage a table which would keep the lookup of the public and private IP and manage the setup for translation within the IPv4. And also it could be the same device that we can now use when we want to tunnel and use the IPv4 and v6 devices. So we can have a NAT4 address inside while we can present a NAT6 or IPv6 address to the outside world. And we can even facilitate overlapping addresses in a much more easier fashion. And if we see that a NAT is becoming a bottleneck, we can instantiate a new instance of a VM to take over and enable that we can scale elastically the kind of functions and run them in our hardware. And likewise, when I mentioned about the routers, we can think of open source control plane that we can build using the Quagga and Linux framework. And we could also build optimized data planes to facilitate more performance-oriented operations, which we will look at the data plane DPDK in the next lecture. Nonetheless, what we have really tried to achieve when we rethink of the network infrastructure that used to be around prior to NFV, what we would see is at the bottom we have the hardware infrastructure, which consists of the rack, cable, power, cooling to run the hardware infrastructure, consisting of the compute nodes or compute hardwares, x86 machines or any ARM machines or any of the servers, the switching infrastructures like routers, the switch devices, and the network infrastructure that encompasses variety of the middle boxes, which used to be the core at the hardware. And on top of these, we used to have the hypervisors, OS, and applications run. Now we have taken out these network infrastructures and moved them into the software layer. That is, now you can think of the infrastructure as just the compute and switching infrastructure that is there as hardware, and all the network infrastructure which were the hardwares earlier have now moved to a software network functions that would run on top of the same compute infrastructure. And this shift is exactly what NFV has enabled, and this shift has also led to a lot of innovations that we can think. So now when we see these network functions, the next immediate question would be, how do we deploy them? And what we have started earlier was the dedicated hardwares. Now we want to get rid of these dedicated hardwares and run on top of the commodity hardware. So one of the most simplest approach would be, we have a dedicated commodity server, which is running a server host OS and comes with the associated binary and libraries. And we deploy the network function as a process that would run. So consider this as a Linux box, and I'm running an application like Quagga on top of this Linux box. So that is one of the most simplest implementations that we can have. So here we are running the network functions directly on top of the physical hardware. But with NFV, we want to bring in the virtualization, and with the virtualization, what we can think of as the most common means to deploy is as a traditional virtual machines. And here what we mean is, we create a virtual machine on top of the physical infrastructure through the use of the hypervisor, and run our applications or network functions as an application within this virtual machine, which would have its own guest OS that would run on top of the hypervisor. And this facilitates at most isolation, the maximum isolation, and ensures that these virtual machines can be spawned and run easily. But these are in a way heavyweight, because we are now trying to maintain a guest OS, the binaries that are needed for that virtual machine to be run on a single hardware. And they are more intensive in terms of the memory and storage. And what we have seen as a shift in this virtual machine model is the lightweight containers. So we could even build our NFV infrastructure, the virtualized infrastructure, to run these containers, wherein NFs can be thought of as the applications that are run within a container, and the container as a scope provides the isolation for that particular application, but it would reuse the same underlying host OS, and that way these are much more lightweight, and we are able to deploy these containers in a much more faster way. That means time to start or time to spawn a new instance would also be greatly reduced when it comes to the containers model of running these network functions. And there was also an interesting path that the researchers proposed, and what we call as the unikernels. Here, think of unikernel as a dedicated kernel on which is just doing one function at a time, and that's exactly our network function. So the unikernel app and host OS are basically the drill down or a very thin or a lightweight host OS and app which just do the function that we want. So think of these as what we can see when we want to run very specific code and just do a particular job alone. And because these are now softwareized in terms of what we would want to run, we can run much more of these unikernels on a same server, so that we are able to scale a lot more than what we would be able to scale with VM and containers, given the limited resource constraints that we may have. And these also unikernels make it a single address space, wherein if something fails, it's easier to respawn another instance or update the state much more easily. And these unikernels are also called as the library operating systems. And one of the most celebrated work in this is the Click OS as a means to develop the network functions using the Click OS infrastructure as a unikernel. To summarize, what we have seen is the evolution of the NFV framework and the reference architecture. And for each of the reference architecture, as it evolves, we need standardized definitions of what interfaces we are going to operate. And the slide here precisely shows what are all the IIT NFV groups, ISGs, deliverables which have enabled us to build this abstractions and build these reference points for implementing the open standards. And you can see that we started with just the 6 of these specifications and documents, but these have culminated to more than over 30 odd documents that have come up trying to foster the openness and innovation in this NFV infrastructure. I have put the links for those to look at, and in order to access these documents in the IIT, all of these are in public domain, and that would give us a good hint of what the way the evolutions have happened for this NFV just over the last 10 years. So NFV, if we have to understand to the core, we'll have to deal with a lot of terms and concepts to deal with. I've tried to cover some of them and address them in earlier lectures, but some of them we may not have covered, so I've tried to put some of the key terminologies and the concepts that are associated with understanding the NFV for reference in these slides, including the most relevant acronyms that you may see in some of the slides and that you may often encounter in trying to understand NFV. So next up, what we will try to do is we will look into the key challenges. We have looked at how these benefits have evolved from these network functions, but any technology like when we bring, it also comes with its own sets of challenges. So it is also important for us to understand the key challenges that come along with this development and deployment and realization of the NFV framework, and we'll try to do that in the next class.